Hello guys, and welcome to CSES problem set. Today we're going to be solving the first problem. It's called weird algorithm. So once you actually look at this problem, you realize that this is just the collapse conjuncture, and we've seen this problem before in Project Euler 14 if you actually follow my YouTube channel. So what we're going to do is we're going to solve this problem, and then I will try to optimize the Project Euler solution that I provided before, since we're looking at the same problem, because I think when I did submit the problem, I didn't really think about the problem that deeply and probably missed the caching part of it. So I'm going to go ahead and implement that. So let's go ahead and solve this problem. Once you go to submit, you can pick the language that you're going to be working with, and this is probably a competitive programming type website. I'm going to be doing most of the solutions in C++. If there are certain features within our language that are much better implemented, then I will use those. Typically Java is fine, but this problem is easy enough where we can just run the algorithm in C++. So what I've done is I've created a C++ project, and I've created a solves CPP file in there, and we're just going to go ahead and implement the algorithm for it. So for this problem, what we need to do is that if the number is actually even, then we have to multiply the number by 3 plus 1, and if it's odd, we have to divide the number by 2. So if we actually follow this, we can see that 3 is actually odd, so we multiply 3 by 3 plus 1, that gives us 10. We divide 10 by 2, that gives us 5. We multiply 5 by 3 plus 1, that gives us 16. We divide 16 by 2, that gives us 8. 8 by 2 gives us 4. 4 by 2, that gives us 2. 2 by 2, that gives us 1. So this conjecture, which was given a long time ago, says that if we're given a number, this is a positive number n, then we're going to end up at 1 eventually if we follow the sequence, right? If the number is odd, we multiply the number by 3 plus 1, and if it's even, we divide the number by 2. You always go down to 1. So let's go ahead and implement the solution for this problem. So what we're going to do is include some preprocessors, and I'm just going to do IO stream, and we're going to go ahead and add the namespace. I'm going to go ahead and create my own type. F. Since it's going to be all positive numbers, we can use an unsigned long. The problem is because if we don't use an unsigned long, we will not be able to go over numbers that are 10 to the 6th power. So this is our cap here. All right, so we need to use long. That's fine. All right, so what we need to do is let's just create the algorithm using main. Alright, so what we need to do is create a variable. We'll call this n, and we need to go ahead and take in our input. What we need to do is output n, because we're going to go ahead and mutate n once we start looking at the while loop, so we won't be able to actually print out the first value. So we need to take care of that outside of the loop. And the next thing we want to do is actually implement the loop. So we'll say while n is greater than 1. What we need to do is mutate n, so say n equals end and 1. So if this is actually odd, what we're going to do is multiply, so we're going to say 3 times n plus 1, and if it's actually odd, then we're going to go ahead and right shift n by 1. Alright, so next thing we're going to do is just print out n and space. And we're pretty much done with this algorithm. So what we're going to do here is just go under debug here. This comes up from the other screen. And we're going to put in 3, and we should get our sequence of values here. So we get 3, 10, 5, 16, 8, 4, 2, and 1. Let me go here for a second and open this in Explorer so I can just copy this file and paste it to my desktop, so that way I don't have to actually search it. Alright, so I'm going to go ahead and close this down because we no longer need it. We're going to go back into problem set here, and we're going to go to submit. We're going to go to browse. I'm going to pick the source.cpp file, open that up, and we're going to pick C++17 and submit. And you guys can see that all of our solutions are accepted and we're good to go. So now what I'm going to do is actually talk about the project Euler question. So I saw this problem sometime in 2018, I think, and I didn't really pay much attention to the collapse conductor. I only came to know about that after a while, that you can actually improve the solution, but I didn't really implement one. I haven't even implemented one, but I just have an idea of how we can do it. So for example, let's say that we're at the value 20 and we know that the next value is 10. If we already computed 10 before, what we can do is we can actually cache the value for 10. So the value for 10 will be 1, 2, 3, 4, 5, 6, 7. So if we're at 20, we just get the 7 count plus 1, that gives us 8, right? So what we want to do is just implement the solution as we would regularly, and then we will figure out how the caching actually improves the solution. So for this problem, we have to find the longest chain under 1 million. So for this, I will be going back to Java because I already created a solution in Java and I want to stick with that. So what we're going to do is create a new Java project, and I'm going to call this one Euler 14. No, I'll just leave it at Euler 14. That's fine. And I'm going to go into presentation mode for now. All right. So what we're going to do is we're going to implement the solution first, and then we're going to figure out how caching kind of improves the solution by maybe just running, taking the time, an average time, something like that. All right, so let's get started. So the first thing we need to do is just create a function that we will need to actually compute the chain. So I'm going to call this one compute, and you should take in a long, call this one n, and we could implement this. So the first thing we need is our counter variable. I'm going to call this cn. This is going to equal to 1. The reason why it's 1 is because we still have to account for the first value that we're going to mutate. So we can't mutate the first number unless we're in the loop. So we need to account for that. Secondly, you can just go ahead and create a while loop and say while n is greater than 1. Then we need to go ahead and implement this. So we're going to say that n is equal to and 1 is equal to 0. That means that it's odd. So let's go ahead and right shift n by 1. Else we're going to multiply n by 3 plus 1. All right, and then next thing we want to do is increment our counter. And then we can go ahead and return our counter. So this is if we didn't apply caching to it, all right? All right, so next thing we want to do is actually compute for the longest chain. So we're going to create another variable. Let's call this one chain. And for this, we need can create a final int, call this one limit, lim, it's going to equal to 1 million. And we need to compute for we need to get the max value. And for now, let's set it to 0 and the max chain, which we're going to set to 0 as well. You can then create a for loop and say for. And since I'm passing in a long up top, I'm just going to create this as a long. Call this one n. It's going to equal to 1 Well, for this problem, we can actually start and add 13 because it does give us 13 as the base. So we can start it at 13, and then we can say that while n is less than the limit, do plus n. All right, and we could implement this. So just what we need to do is get the current chain for the value that we're looking at, and this is going to be the compute, and we can pass an n here, and then we can check to see if the current is greater than the max chain. All right, and if that's the case, then we have to set the max chain to the current value and the max value to n. But we need to go ahead and do a cast here. So we do n. So since I'm going to be using this casting a lot, I'm going to go ahead here and just create another private method. So I'm going to call it C for cast. So I'm just going to call it. I'll call it C for cast. It's going to take me along, and I'm going to call this one n, and we're just going to return cast. All right. So, all right. So now we create a cast here, and I could just call CN, and that makes it better. All right, and once we're done with that, we need to actually return the max value. So let's go ahead and create min for this. And what we need to do is let's take the start time and the end time. So long s is going to equal to system current milliseconds, and we're going to go ahead and use our chain function, and we're going to get the end time. So actually we could just do SRT, and we're going to do so system current milli minus start. All right, so if we do this and we run our main method, so you guys can see that this actually gives us the answer for this problem, which is the same as this one provided. You can see it's this answer, and the time that it took was around 342 milliseconds. All right, and we can run this again to see if it's kind of consistent. We could run this multiple times by creating some test classes and running this multiple times and getting the average of that. So on average, it should be around like 200, 198. So let's say about 198 to about 210, right? So let's make it around 200. All right, so let's go ahead and improve on this. So the thing is, you can actually use maybe a map, or you can probably use a map on this, and you can store the subproblem. But I figure it's probably better to store an array. That way, just the checking should be O of 1, and the insertion should be O of 1, and then we can actually just reduce the size of the numbers that we want to check to make this a little bit quicker. So up top, what we can do, let's create a private static final int, and let's call this limit, and we can make this something like this. Yeah, so I think it should work for 25, 26 maybe. Let's try 26. So we want to create an array that we're going to use this to cache things in, but we don't want to make this so big that it will not fit within, the values will not be able to be cached, because we need to actually use the spot to actually cache the value. So if the value is way too big than the size of an actual int, we won't be able to use that, store that value, and that would create problems when we try to access that index location. So we need to actually create some limit. And the next thing we want to do is create an array. We call this one cache, which is equal to new int array, and we're going to pass in a limit here. So once we have this, we can do is we can come here and we can say that if, all right, n is less than the limit, all right, and if cache, and we're going to go ahead and cast, since n is a long, we have to cast that to an int, is if that is and if that is greater than 0, that means that we've already cached a value in there. So for this time, we actually need to go ahead and check one more thing. Well, because we're going to mutate n, we need to actually keep a copy of n, because we need to cache the actual value that we have up top, because we're going to have the subproblem plus the actual count. So for this, we're going to say long omega cp, and this is going to equal to n. So we're going to actually make a copy of n, and here we're going to say that if cp is less than the limit as well, that means that we can actually store cp within our cache array here. So we're going to say cache, and we need to go ahead and cast cp, and we're going to go ahead and make that equal to our current count value plus the cached subproblem for this particular number. So we need to go ahead and actually go ahead and pass in n here. All right, and then next what we want to do is actually return cache, and we're going to go ahead and convert cp here. All right, so we're just going to go ahead and return that specific count for that value. And also, if we're outside, once we've, let's say for example that we're running the value 2, for instance, and we didn't have the value 1 already cached, so now we actually need to go ahead and cache 2. Okay, so what we're going to do is we're going to say the same thing. We're going to say if, right, cp is less than the limit, then cp is within our cache index or subscript location. So what we can do is we can say that cache, and the same thing, we need to go ahead and do a cast. So we're going to cast cp, and that's going to equal to our counter. All right. So now what we've done is we have created a container that's going to cache part or subproblem of our actual sequence. And if we find that sequence, what we're going to do is just take the current count plus that sub part, and then we're going to go ahead and return the entire solution for that value, for that chain. So now if you go ahead and just run our algorithm without changing anything, you can see that this only takes around 45 milliseconds.